Good evening, Loughton. A pleasure to talk to you once again. The beginning of everything, as you can see from the subtitle, I'm talking about the origin and the very early history of the universe. When we look out into the universe, we see a lot of galaxies spread, not necessarily uniformly. If we look at this sky survey, it looks like a bit of CGI, it looks artificial, but in fact, you should treat this more like a 3D atlas. A lot of the positions of galaxies in the sky have been mapped out and their distances have been measured, and that has constructed this 3D atlas. And this is a sort of a fly-through of our local universe. And it shows us that the galaxies, well, apart from the fact that there are lots of galaxies out there, it shows us that they aren't all uniformly distributed. They seem to be clustered into clusters or superclusters of galaxies. There seem to be some regions of the universe which appear to be almost empty. And when galaxies do cluster together, they often cluster together in lines or filaments in a structure that we call the cosmic web. It would be nice to understand where all this stuff comes from. If there really are billions of galaxies out there, and the best guess is probably a few trillion galaxies in the observable universe, and it's probable that each of these galaxies has got many, many billions of stars. Where does all this stuff come from? All of these galaxies, all of the stars, all of the gas, all of the dust that we can see. Where did it all come from in the first place? That's what we're looking at this evening. So we've often seen this sort of image, a Hubble deep field. In this particular case, we've picked up perhaps one or two stars. In the top, there's a couple of stars. There's maybe a star close to the middle and one near the bottom. So we've picked up perhaps 4 stars that are in our own Milky Way galaxy. Everything else you can see in this image is another galaxy, probably at a considerable distance. This is only a very small patch of sky, but if we extrapolate from images like this to the whole sky, it would appear that the observable universe is full of perhaps a few trillion galaxies. So I'm talking about the creation of the universe. When did this happen? To the best of our understanding, it happened about 13.8 billion years ago. How long did it take to make the universe? Well, it took about 3 minutes, and I'll explain why that 3 minutes is significant when we start looking at the timeline of the creation of the universe. I often get asked, where did it happen? As if you can look out at some part of the sky and see where the Big Bang happened. No, that isn't the way it works. The Big Bang was the origin of everything, the beginning of everything, and therefore the creation of the universe happened everywhere, as a part of definition, if you like. We can't simply look to one part of the sky and say it happened over there. Why did it evolve the way it did from creation to where we are now 13.8 billion years later? Well, it evolved the way it did because of the laws of physics. How do we know all this? Same answer, because of the laws of physics. In other words, what we're trying to do is understand the rules of the game. The universe was created and the universe ended up looking the way it does now. But what are the rules of the game that dictate how it started and how it ended up looking like this? It's a bit like saying, if we were to watch a game of chess, can we work out what the rules of the game are? If we were to take a static image like this and ask somebody who's never played chess before, can you tell what the rules of the game are by looking at this chessboard? The answer is probably no. It's too confusing. It looks like there's 2 types of pieces, one silver coloured and one gold coloured, so maybe it's a game between 2 people. But they're all different shapes and they're all in different positions on the board. One of them seems to have fallen over. We can't tell what the rules of the game are by looking at a snapshot like this. And similarly, we can't tell what the rules of the game are for the universe simply by looking at, for instance, a snapshot of a galaxy. The universe doesn't come with a manual. So we can't look up how it came to look like this. How did it start and how did it end up looking like this? A snapshot of a galaxy doesn't tell us much in that sense. We can't watch the galaxy evolve. We can't even watch the galaxy rotate in the sense that it would take hundreds of millions of years to rotate just once, and we haven't got the patience to sit and watch it to try and figure out what it's doing. But there are alternatives. Just like with the chess game, a single picture doesn't help. A video would be better to watch two people playing chess, and if we watched a video of a game in progress, we could get a pretty good idea of what the rules would be. But we can't do that with galaxies and the universe in general because we simply don't have the time. We can't wait for billions of years to watch it evolve. The alternative is to say, well, can we at least take pictures of 1 million or 1 billion games of chess all being played out at the same time, not watching any particular game to completion, but can we look at snapshots of 1 billion games of chess and from that deduce what the rules of the game are? So instead of looking at one galaxy and trying to deduce what's happening by watching it, can we take images of thousands or millions or perhaps even more galaxies, all at different stages of evolution, and from that work out the rules of the game? Remember, because the speed of light is finite, the more distant galaxies, the light has taken a while to reach us, and so we're looking at them at earlier stages of evolution. The further away a galaxy is, the further back in time we are looking. So even a single snapshot like this can be useful because if we can work out the distances to these galaxies, we are looking at the closer galaxies as they are now and the more distant galaxies as they were sometime in the past. So from lots of images like this, we can start to piece together the rules of the game. In other words, the laws of physics that specify how the universe ended up looking like this. This is, of course, just an equivalent from the James Webb Space Telescope. We've taken quite a few images like this of distant galaxies to be sure that the original Hubble Deep Field, for instance, wasn't just a fluke. The fact that we got a few thousand images in one image wasn't a fluke. We can look in any part of the sky over a small range and see thousands of galaxies, and from that we deduce what the overall structure of the universe must be. But if we look on a much more local scale, for instance, this little part of the galaxy we're looking at here, perhaps you recognize it as part of the constellation of Orion, we might look at this and say, well, surely things are just far too complex. Just look how much complexity there is in an image like that. The Orion Nebula, the Great Nebula in Orion, is off to the right of the image. There's the Horsehead Nebula at the bottom. There's a huge amount going on here. Isn't it simply far too complex to work out what the rules of the game are? Well, if we use an analogy and think about a mathematical collection of pixels, here are a lot of coloured pixels that have been generated by a particular mathematical formula. And the colour of each pixel, here you're looking at perhaps a few million pixels, depending on the projector that you're using to generate the images on the screen that you're looking at. If we wanted to, we could zoom in as much as we like, and we will continue to see more and more and more detail the more we zoom in. You might say to yourself, well, surely a lot of these things are just repeating. A lot of these patterns, these motifs, aren't they just repeats of each other? Well, no, they're not. They might look similar, but the same pattern never repeats, no matter how much you zoom in to the detail of this mathematical set, which happens to be called the Mandelbrot set. Just like we might have many billions of stars in a galaxy, they might all look similar, but none of them are identical. The same is true here. We have patterns which do not repeat. Some patterns look similar to other patterns, but none of them actually repeat. So in a sense, this is an infinitely complex pattern. This is an infinitely complex set of pixels that can be generated by a mathematical formula. How complex, how complicated is the formula that was needed to generate each and every pixel, not just the few million we're looking at, but the trillions of pixels in the entire Mandelbrot set. How complex is the formula? It's that. I'm not going to explain z equals z squared plus c. Suffice it to say, that formula generates everything you're looking at and trillions of times more complex patterns that could be found by zooming in. So the point I'm making is, just because it's complex does not mean it's incomprehensible. I like this quote from Einstein: "The most incomprehensible thing about the world," and for world, read universe if you wish, "the most incomprehensible thing about the universe is that it is comprehensible." There's no particular reason why we, as a species of ape who came out of the trees a few million years ago, should be able to comprehend how the universe works and how the universe came into being. And yet, despite its complexity, it is possible to comprehend many of the concepts underlying the universe. So the flow of thought that helps us understand how the universe put together is something like this. For a while now, we've known that galaxies are moving away from each other. That's now something like 100 years old, this observation. If galaxies are moving away from each other, we come to the conclusion that the universe is expanding. If we combine that with our understanding of how matter is put together by doing experiments here on Earth, for instance, we can do experiments by smashing atoms together and finding out what they're made of and understanding the fundamental particles which makes up everything around us. So experiments such as the Large Hadron Collider allow us to understand the basic properties of matter. But to make any progress in saying we can observe the universe and we can do experiments in the lab, but we can't make any progress with understanding the universe unless we make a couple of rather important assumptions. We have to assume that the laws of physics are immutable. We have to assume the laws of physics in one place are the same as the laws of physics in another place. If that was not the case, if the laws of physics in England were not the same as the laws of physics in France, or Australia, or Alpha Centauri, or the Andromeda Galaxy, if the laws of physics were different everywhere, then we would never be able to make any sense of the world around us. And the same is true of time. If the laws of physics now were different to the laws of physics yesterday, and we don't know what the laws of physics are going to be tomorrow, then again, we can't make any progress. The only way we can understand the world is to assume that the laws of physics as we understand them now are the same everywhere and have always been the same and will always be the same. If that is not true, then we have no hope whatsoever of understanding anything. So that assumption, or those two assumptions, have to be made. So if we observe the universe and we do experiments in the lab and we make those two assumptions, then we come to the conclusion that the universe was created in a very hot, dense state 13.8 billion years ago, and it has been expanding and cooling ever since. We'll see the details of that shortly. But the big question we're trying to answer is, okay, the universe was created a long time ago and is expanding, but where did all the matter that we see today come from? Where did all of the galaxies and the stars and the gas and the dust and everything that we see that's out there, where did it all come from? How far back in time can we go using our understanding of the laws of physics? In other words, how far back in time can we go before we say we really don't know what the rules of the game were back then? We know the universe is 13.8 billion years old. Can we go back to the first year of the 13.8 billion year history of the universe and say, yep, we've got a firm grasp of what was happening back then? Yes, no problem. Can we go back to the first day? Yes. Can we go back to the first hour? Yes. Can we go back to the first minute? Yes. Can we go back to the first second after the Big Bang and say we've got a fairly good handle on what was happening? Yes. What about the first millisecond? Yes. What about the first microsecond? Yes. What about the first nanosecond? Yes. What about the first picosecond? No, not really. There's a watershed there. Before the first picosecond, before the first 1/1,000,000th of a second, we don't really know what was happening. We cannot be sure that we understand the rules of the physics that applied back then were as we understand them now. After that first picosecond, after 1/1,000,000th of a second, everything is reasonably well understood. Yes, I'm not claiming we understand absolutely everything, but everything after a picosecond, we are on relatively firm ground. And I'll explain why that picosecond is important shortly. So that was a rather long, rambling introduction to what it is I'm talking about this evening. I was trying to set the scene so we understand what it is we're trying to do. The next slide is going to contain a few basic ideas which allows the structure of the remaining slides to make, hopefully, a bit of sense. And then I'll be looking at what happened in the first fraction of a second, the first few seconds, the first few minutes, and then, to avoid being here for the rest of time, we're going to change gear and accelerate a little into the future, and then quickly talk about what's happening up to 380,000 years later, and that's not a random number, there's a particular reason for choosing that time. And then again we're going to change gear and go fast forward up to the present day and think about the next 13.8 billion years. So that's what we're going to be doing. So first, a few basic ideas. Some of these ideas you probably already know about, some of these ideas may not be so familiar to you. Firstly, we are made of atoms. I hope that comes as no surprise to anybody in the audience. Atoms are structures which have a positively charged nucleus and a lot of negatively charged electrons buzzing around them. So atoms are not so-called fundamental particles, they are made of other things. We found that out quite a long time ago. If you apply a little bit of energy, you can separate the constituents of an atom into the positively charged nucleus and negatively charged electrons. As far as we are aware, electrons are not made of anything. They are fundamental particles. They don't have any inner structure. You can't take an electron, cut it in half, have a look inside and see what it's made of. It's not made of anything. It's just an electron. So we call those fundamental particles. However, the nucleus of an atom is not a fundamental particle. It is made of something else. And we found that out about a century or so ago, that the nucleus of various atoms are made of something else. We can take a nucleus and, given enough energy, we can separate it out and find that it's made of protons and neutrons. These are the names of particles that we give for the positively charged components of a nucleus. We call those protons, and the particles that have no charge, we call those neutrons. Neither protons nor neutrons are fundamental. They are made of something else. And again, this was found out in the early part of the last century. So for instance, a proton is made of three particles called quarks. A bit of a silly name, but we have to live with that now. Quarks apparently are fundamental particles. To the best of our knowledge, they are not made of anything else. We don't think we can take a quark, cut it in half and see what's inside. So a group of three quarks is what we call a proton. Neutrons are also made of quarks. I'm just using the proton as an example here. So this sort of Russian doll. Atoms are made of other things, like nuclei. Nuclei are made of other things, called protons and neutrons. Protons are made of other things, called quarks. And to go down this ladder takes more and more energy. It takes more energy to split a nucleus than it does to split an atom. It takes a lot more energy to look inside a proton. So there's an implicit energy scale from low energy at the top to high energy at the bottom. And to a physicist, low energy and high energy are basically the same as low temperature and high temperature, because temperature is really just a way of measuring the average amount of energy that all the particles have in a particular state of matter. And remember, we conclude that the universe was born in a hot, dense state and is expanding and cooling. So if it's low energy at the top and high energy at the bottom, then that's equivalent to hot at the bottom, cold at the top. So there's an implicit timeline running from the bottom upwards, because the universe was made hot and is cooling down. So we can conclude that the universe was made from the bottom up. You can't expect three quarks to get together and make a proton in the early universe when the universe is so hot. The quarks have got so much energy, they can't possibly make a proton because they've got so much energy, the proton would simply fly apart. Similarly, you have to wait until the universe has cooled down until the protons and neutrons can get together and make a nucleus. If you try and put protons and neutrons together when the universe is too hot, they simply have too much energy and the nucleus falls apart. Similarly, you have to wait even longer until the universe has cooled even more before the nucleus can get together with electrons to make atoms. If you try and make atoms too early in the universe, the nucleus and the electrons have got so much energy, the atom simply falls apart. So there's a timescale and a structure, a Russian doll type structure, in which we're going to make protons and then nuclei and then atoms and then molecules and then eventually us. So that's the process that we're going through. So let's have a look at the timeline. Now, the most contentious issue is what happened at time t equals 0. What happened at the instant of the start of the universe? And the simple answer is we don't know. Science cannot provide a definitive answer. Perhaps, this is simply speculation, perhaps it was a quantum fluctuation. Quantum theory, the idea of what happens on very small scales, we can study very small systems, and quantum theory, which has been around for about 100 years, says that very odd things can happen on small scales. For instance, you can borrow energy from nothing. Now that sounds really weird that you can get energy from nothing, because classical mechanics, good old Isaac Newton, says you can only turn energy from one state into another. You can't get it from nothing. Well, quantum theory says you can. Now, I know that sounds weird, but yeah, quantum theory and quantum mechanics, how we put together quantum theory, that is weird. That's the subject of an entirely different talk, and I'm not going to go into details. So quantum theory does allow you to borrow from nothing. How big can you have a quantum fluctuation in which you borrow effectively energy from nothing? How big can that fluctuation be? Well, the amount you borrow multiplied by the length of time you borrow it does have an upper limit according to quantum theory. It's like going to a bank and trying to minimize the amount of interest you pay, so you either borrow a lot of money and pay it back very quickly, or you borrow a smaller amount of money, in which case you can have longer to pay it off for the same amount of interest. It's a little bit like that. Energy that you borrow times the time that you borrow it for has an upper limit. So the bottom line is, if that is in a sense an explanation of where the universe came from, that we borrowed it from nothing, it matters as to how much energy we've borrowed. What is the total energy of the universe? Well, we're not too sure, but we can estimate it. Because all of the gravitational energy in the universe is negative, and all of the mass energy in the universe is positive, and when we add it all up, as best we can tell, the answer seems to be 0. So if the total energy in the universe is 0, then we've got plenty of time to pay back the loan, and the universe won't mind that. Quantum theory says that's fine. Now, I'm sure that all sounds like a complete fudge, but let's face it, most of quantum theory sounds like a fudge, but it's been with us for 100 years now, and nobody has shown that quantum theory is wrong. So maybe this is an explanation, but I repeat, it is only speculative explanation. Let's move forward now to this time scale. 0.000, you can count them yourself, 1 seconds. At the unimaginably early time of 10 to the minus 35 seconds, the universe has expanded from a point to something about the size of a golf ball, by which I mean everything that we currently see in the observable universe. The observable universe is a sphere approximately 100 billion light years in diameter. Everything that we currently see in the observable universe used to be a lot closer together, centimeters apart. Now, it's difficult to imagine everything from 100 billion light years being compressed into something the size of a golf ball. But, to the best of our knowledge, that's how it started out. This golf ball, just like a real golf ball, isn't totally smooth. I don't mean it has dimples in the surface like a golf ball, that's just an analogy, but it isn't perfectly smooth. This universe, as it were, this observable universe in which everything is now a lot closer together, isn't perfectly uniform. It has small fluctuations, small variations in density and temperature, a little bit like the dimples in a golf ball. Eventually, when the universe expands into a much bigger structure, these dimples will give rise to the variations in density spread across the universe that will result in the formation of large-scale structures such as galaxies, clusters of galaxies, superclusters of galaxies. We'll see a simulation of that a little later in the talk. We're now moving forward to 1 picosecond, 1 trillionth of a second after the Big Bang. The universe has now expanded to the size of the solar system. Yes, I realise the solar system doesn't yet exist, but that's just giving you an idea of the size. It's expanded in a tiny fraction of a second from something the size of a golf ball to something the size of a solar system. In other words, a few light hours or so in size. So the universe has expanded much faster than the speed of light. Don't worry, it's allowed to do that. Nothing can move through space faster than the speed of light, but space itself can expand at greater than the speed of light, and indeed is still doing today. The temperature at this point, 1 picosecond after the Big Bang, the temperature has fallen to about 10 to the 15 Kelvin. And the energy of each of the constituents, from the energy that we've borrowed, we can make as much matter as we like. I'm calling it a quark soup. It's actually a soup of lots of quarks and electrons and loads of other particles as well, but I don't want to keep saying that, so I'm simply going to call it a quark soup. Having borrowed energy, we can make matter, and we've got a lot of particles in this quark soup, and at this particular point in time, the energy of each of the constituents in this soup is roughly equal to the energy of the particles in the Large Hadron Collider. In other words, if we want to see how does matter behave when it's at this sort of temperature, we can do the experiments in the Large Hadron Collider. We can obtain those sorts of energies by accelerating particles, accelerating protons and smashing them into each other. We can recreate the conditions of the energy of the particles at this particular point in time. This is why we say from 1 picosecond onwards, we can test any idea we have about how the universe is behaving, because we can reproduce the energies in a particle accelerator in the laboratory. Prior to this point, the energy of the individual particles was so high we can't reproduce those situations. We can't reproduce the conditions, and therefore we cannot test any ideas we have with experiments. And if we can't test ideas with experiments, then it remains speculation. It remains purely a hypothesis. But from this point onwards, we can actually do real tests by seeing how does matter actually behave when it has this amount of energy. So that's why the picosecond is the watershed. It's the point at which we can access the energies in laboratory experiments. Matter and antimatter are continually exchanging back and forth with energy. We've borrowed energy from nothing, and we can convert from energy into matter and antimatter because E equals mc squared, and so we can take energy and make matter, and we can take matter and make energy. Originally, when we take energy and make matter, we make matter and antimatter in equal amounts. Antimatter is just the opposite, if you like, of matter. If we think of a particle like an electron, it has a cousin, if you want to think of it that way, which has all the same properties as an electron, except it has the opposite charge. If you like, you can think of it as a positively charged electron. We call it a positron, and it is the anti-electron. It is the antimatter equivalent of the electron. Every particle has an antiparticle equivalent. And when energy was used to make matter, it also made an equal amount of antimatter. And we can represent this graphically. I don't know how to represent energy. I've just used a large capital E to represent a certain amount of energy. Energy can make matter and antimatter. Probably not a tangerine and an anti-tangerine. It'll probably make a quark and an antiquark, or an electron and an anti-electron. The point is, it doesn't matter. Energy can make some particle of matter and its antimatter equivalent. And the matter and antimatter will then almost immediately annihilate and produce energy. And that energy can then again make matter and antimatter, but it won't necessarily make the same particle and antiparticle that it made last time. It could make a completely different particle and antiparticle. Okay, it won't be a hot dog and an anti-hot dog, it'll be something and its antimatter equivalent. The point is, this is going backwards and forwards, energy to matter and antimatter, back to energy, back to matter and antimatter. This process is going backwards and forwards, over and over and over again. Somehow, via a process we don't really understand, matter gained a very small excess over antimatter. We would naively assume that when you start with energy, you will make equal amounts of matter and antimatter, but somehow they got out of balance. So on this sort of timescale, we know that more matter than antimatter was made. Now, in this particular graphical representation, I'm implying that there was a 10% excess, something like 10 bits of matter for every 9 bits of antimatter. In fact, the asymmetry, the imbalance, was nowhere near that large. It was not 1 part in 10, roughly speaking. It was more like 1 part in a billion. But it's rather important because when it came for matter and antimatter to annihilate, then various particles of matter annihilated with their antiparticle equivalent and produced energy, ultimately in the form of radiation. So photons of light, particles of light. But of course that meant that we've got a bit of matter left over, because if you generate more matter than antimatter, then when all the matter has annihilated with all of the antimatter that's available, you're left with a tiny amount of matter left over. So that's why we live in a universe which has an awful lot of energy floating around in the form of light and some particles of matter. And that little bit left over, that 1 part in a billion, is everything we see. It is every galaxy, it is every star, it is every speck of dust, it is every atom of gas, is that 1 part in a billion that was left over when the matter and antimatter annihilated. And we can double check that by basically counting, or at least calculating, how many particles of light, how many photons of light are out there compared to how many particles of matter. And it turns out there are 1 billion photons for every particle of matter. In other words, there are 1 billion of these for every 1 of those. We're now moving forward to 1 millisecond after the start. So t equals 0.001 second. Matter and antimatter are continuing to pop into and out of existence. Protons and neutrons are made from quarks, and we've got a lot of quarks floating around in this soup of matter that's being made. And whenever we have 3 quarks that get together in a certain pattern, we call that a proton. So on the left-hand side, a bag of 3 quarks, and I'm not going to explain why they are labelled U and D, and I'm not going to explain why they are coloured red, green and blue. Let's just accept for the time being that a particular collection of quarks is called a proton, and a slightly different collection of quarks is called a neutron. So a neutron and a proton are just the labels we use for a bag of 3 quarks that are these 3 and a bag of different quarks. And if quarks are changing into energy and energy is changing into quarks, then effectively protons can change into neutrons and neutrons can change into protons. And so protons and neutrons are continually transforming into each other back and forth at this sort of time, 1 millisecond after the start. That will continue until we reach about a second or so after the start. The universe is now cooled because all of this time, remember, the universe is continuing to expand. After 1 second, the universe is expanded to the point where it's cooled down to about 1 billion Kelvin. And it's now too cold for protons and neutrons to readily swap backwards and forwards. When there's enough energy for quarks to change into energy and energy to change into quarks, when there's enough energy around, protons and neutrons are continually swapping backwards and forwards. But once the universe is expanded to the point where it's cooled down a bit, then protons and neutrons find it more difficult to change into each other. Now, protons are a little bit lighter than neutrons, and in this talk I'm using red balls to indicate protons and blue balls to indicate neutrons. Protons are a little bit lighter than neutrons by about 1 part in 1,000. How do we know that? Because we can measure them in the laboratory today. And we think that protons and neutrons today are no different from protons and neutrons 13.8 billion years ago. And indeed, no different from protons and neutrons will be trillions of years from now. So if protons are a little bit lighter than neutrons, that means protons outnumber neutrons. And it turns out that at this particular temperature, we would expect the ratio of protons to neutrons to be in the ratio of 75 to 25. And here I'm just showing a representative collection of 16 of these protons and neutrons. 12 of them are protons and 4 of them are neutrons. So why should protons outnumber neutrons just because they're lighter? Well, nature always favours the lower energy, or equivalently the lower mass, because mass and energy are in a sense equivalent. Another way of thinking of it is if the universe is making shed loads of protons and neutrons, and protons are a little bit lighter, well, they're easier to make. If they're easier to make, you make more of them. And we can do calculations based on our understanding of the laws of physics, based on our understanding of the rules of the game. We can calculate that at 1 billion Kelvin, we would expect that ratio of how many protons to how many neutrons, based on this small mass difference, to be this ratio, 75 to 25, 12 protons for every 4 neutrons. We can now go forward from a second to the first few minutes. We're now talking about a few hundred seconds after the start, after the creation. We know that neutrons are unstable and will change from neutrons into protons. How do we know that? Because we can measure them in the laboratory, and a neutron on its own, not part of the nucleus of an atom, but a neutron on its own that's not part of a nucleus, will change into a proton. It'll take a few minutes to do that, but it will change. And if that's the behavior of neutrons now, we assumed that that was the behavior of neutrons in the past. So neutrons will change, some neutrons will change into protons. It'll take a few minutes, and the ratio of protons to neutrons will change from 12 to 4. It'll now be 14 to 2, because 2 of those blues that were here have now changed to reds. They won't all change because they don't have time to do that. After a little while, the universe is too cold for them to change. The universe, after a few minutes, has cooled down to about 100 million Kelvin. So it is now possible for protons and neutrons to get together. Before this point, if you try and take a bag of quarks that we call a neutron and a bag of quarks that we call a proton, try and get them together, well, they have simply too much energy and they would fly apart. But now the universe has cooled to 100 million Kelvin, it is possible for protons and neutrons to get together. And one of the most stable structures that they would like to produce is this one. It's called an alpha particle. It is 2 protons and 2 neutrons. Again, I'm not going to go into the details of the particle physics, but when you put 2 protons and 2 neutrons together and make a particle of these 4 particles, it is a very stable structure. Protons and neutrons want to make this stuff, so-called alpha particles, also known as the nucleus of a helium atom. But of course, not every proton can marry up with a neutron, because we've got 14 protons for every 2 neutrons. So these 4 particles on the right can marry up to make 2 protons and 2 neutrons. We now have a nucleus of helium. But that leaves us with 12 bachelors. That leaves us with 12 protons that can't find a neutron to marry up to, even though they would dearly like to. So we end up with 12 bachelors, protons, which another word for a proton is the nucleus of a hydrogen atom. So after this time, a few minutes, we end up with 12 nuclei of hydrogen and 1 nucleus of helium. From this point onwards, the universe is too cold to change that. So after about 3 minutes, the relative abundance of hydrogen and helium has been determined. A day from now, a year from now, 1,000 years from now, 1,000,000 years from now, that ratio will still be the same. When we look out into the universe and look at all the gas that's out there, what do we find? The Big Bang Theory predicts that 3/4 of it by mass should be hydrogen and 1/4 should be helium. When we look out into the universe, what do we see? Of all the gas that's out there, we find 3/4 is hydrogen, 1/4 is helium. The fact that Big Bang Theory predicts this ratio gives us some confidence that we can believe what it's telling us. Now, ultimately, hydrogen will be used by stars and they will end up taking individual protons, fusing them together and make heavier elements. But that's a long, long, long way into the future. As far as we're concerned, after 3 minutes, we've made all of the fuel needed to make stars. Nothing of any interest happens for the next 380,000 years. The universe will continue to expand. The universe will continue to cool down. The hydrogen and the helium will get more and more dilute. But nothing interesting happens until we hit this magic point of 380,000 years. What happens at that point? Well, at this point, the universe cools to a temperature of about 3,000 Kelvin. Why is 3,000 Kelvin significant? Well, that's the temperature at which you can expect a nucleus to hang on to its electrons. The electrons are floating around in the quark soup. I've called it a quark soup, but remember it's a soup of quarks and electrons and loads of other particles. Before this point, there was too much energy for a nucleus to hang on to the electrons. The atom would simply fall apart. But from this point onwards, 380,000 years onwards, the temperature is now low enough that atoms can exist for the first time, because nuclei can actually hang on to the electrons. The positively charged nuclei can attract the negatively charged electrons. That's important because now, instead of having a universe full of positive charge and negative charge floating around in a plasma, we now have a lot of neutrally charged, in other words, uncharged atoms. For the first time in the universe's history, the universe becomes transparent. Up to this point, any light that was trying to travel through this plasma was continually getting bounced around by all of the positive charge and negative charge. Effectively, the light was trapped in the plasma. But now the universe has turned transparent, the light can fly around the universe. At 3000 Kelvin, most of the light would have been visible light, with a wavelength of about a micron or so. But remember, the universe has expanded a lot since then. The universe now is about 1,000 times bigger than the universe was at this point in time. So that 1 micron wavelength has been stretched out until it's more like a millimeter. In other words, the visible light has had its wavelength stretched from visible light to 1,000 times longer. It's now microwaves. And that is precisely what we see in the cosmic microwave background. When we look all around us, we see microwaves coming from every direction, roughly the same intensity in all directions. It's been sometimes described as the afterglow or the echo of the Big Bang, because it is the first time we're able to see any electromagnetic radiation that resulted from that very early fireball of the Big Bang. So it's not quite the same intensity in all directions. Here, the small variations have been exaggerated. These variations in intensity, either hot spots or cold spots indicated by red and blue, they're only less than 1 part in 1,000 of the overall intensity. So you could say it's essentially the same in all directions, but in this particular plot where we've taken the entire sky and unwrapped it into a projection so we can see all directions here, we see that there are some fluctuations in the intensity of the cosmic microwave background. And that is precisely because the original golf ball had some fluctuations. The dimples in the golf ball, the variations in density, the variations in temperature of the very early universe, now that the universe has expanded, we see those fluctuations, we see those variations, we see those dimples, in a sense, by these variations in the cosmic microwave background. And that is precisely why there's a lot of interest in looking at those variations. The small variations that we can see in this all-sky map of the cosmic microwave background are telling us about those very early variations in density and temperature in the very early universe. So the more detailed map we have of the cosmic microwave background, hopefully the better understanding we will have of the very early universe. So the existence of the cosmic microwave background is another reason why we believe that Big Bang theory is the right theory to explain the origin of our universe. Not only does it get the hydrogen-helium mix right, it also predicts the existence of the cosmic microwave background. And again, we've known about this for many decades, which is why we believe Big Bang theory is the best theory we have for the origin of the universe. We can get an idea of how we start with the dimples in a golf ball, how we end up with galaxies. We can't see it happening, but we can run simulations. We can start with not the entire universe, because that's a little bit tricky. We can start with a little bit of the universe and say, let's fill it with stuff, but not uniformly. Let's fill it with matter where we have some variation in density, some variation in temperature over a large cube of material, and then we simply let gravity do its stuff and see what happens as the universe expands. If we run this sort of simulation in a computer, this is what we see. The lighter colours indicate denser parts of the structure. So at the moment it's almost a uniform blue with some small mottling which you might be able to see. But when we run the simulation and let gravity do its stuff, we see some parts get more dense and brighter and some parts get less dense and darker. And now we're starting to see a lot of matter clumping together. We're starting to see these white blobs, which are galaxies, and clusters of galaxies and superclusters of galaxies forming. We also notice that the galaxies tend to form along lines, along filaments. We get a web-like structure, and we get large regions, which we call voids, where there seem to be very low densities of any matter forming into galaxies. And this is just like, if you remember, the fly-through that we saw in that 3D atlas right at the start of the talk. That's what we see in the universe around us. We don't see a uniform collection of galaxies. We see galaxies clustered into filaments and a web-like structure, which is simulated by simulations like this. So we can't be absolutely sure, but again, that gives us confidence that if that is what gravity does to a cube of matter in which there is small density and temperature fluctuations across the cube, let gravity do its stuff, it does seem to indicate that we end up with the large-scale structures that we see in the universe around us. If we take just a local map, this is just a different way of looking at it. There's the Milky Way galaxy, and this map shows some of the galaxies around us, a lot of small galaxies in the so-called local group of our immediate neighbourhood. There's the Andromeda galaxy over here on the right, the Triangulum galaxy a little bit further down here, and lots of these small satellite galaxies floating around. From this, because it's a relatively small scale, we can't really see the structure that I was indicating a moment ago. If we zoom out a little bit so that the Milky Way, etc., is now in this region called the local galactic group, now we can see that some of our neighbours are indeed clustered together, such as the Virgo cluster, the Fornax cluster, etc. Notice that these clusters seem to lie on something like a line. That's one of these filaments that we can see in the large-scale structure of the universe. And again, if we zoom out, then this detail we can see here gets blurred together into this region called the Virgo supercluster, and we can see other superclusters dotted around the universe. Again, we see patches, we see filaments, and we see regions in which there appear to be very few galaxies at all, such as here in the top right, the Bootes void, for instance. This is all a consequence of the dimples in the golf ball and ultimately the fluctuations in the cosmic microwave background, giving variations in density which gravity ultimately turns into all of the galaxies and clusters and superclusters that we see in the large-scale structure of the universe. Now that we have hydrogen, and remember it only takes 3 minutes to make the hydrogen, you could argue once those 3 minutes have gone, well, we've now got all the hydrogen we need, and eventually, it'll take a little bit of time, but eventually that hydrogen will be used to fuel the stars. So after 3 minutes, we've got all of the hydrogen atoms that we need to understand what's going to happen in the next 13.8 billion years. That hydrogen is going to make galaxies, which are full of stars. And those stars are going to have planetary systems, so we can understand planets, and we can understand trees and mountains and snowflakes and rainbows and cats and... Okay, maybe not cats. I don't think we'll ever understand cats, but we can pretty much understand everything else. I know I am definitely sweeping over an awful lot of detail, but the point is, if we can understand where the hydrogen comes from in 3 minutes, then everything else follows from that. Yes, a lot of detail of cosmic evolution we are still trying to understand, but in terms of the big picture, we think we understand what's going on. If we try and condense it onto one rather ridiculous timeline from very short times on the left through picoseconds, minutes, thousands of years, millions of years, billions of years, and there's where we are now at 13.8 billion years, a graphical summary of what I've just been saying is that we borrow energy from nothing, maybe, that's a speculation. The universe expands until it's the size of a golf ball after about 10 to the minus 35 seconds or so. And we end up with a soup of matter and antimatter. We're calling it a quark soup, but it's actually lots of quarks, lots of electrons, lots of all the particles and antiparticles that can be made by borrowing energy and then making matter and antimatter. After a second or two, some of those quarks get together and make a bag of quarks that we call a proton, or a different bag of quarks that we call a neutron. Given a little bit of time, like 3 minutes or so, the protons and the neutrons can get together because the universe is now cold enough to allow that, and make the alpha particle structure of 2 protons and 2 neutrons. Any protons that are left over become the nuclei of hydrogen atoms. After 380,000 years, the universe is cold enough for those nuclei, those protons and alpha particles, to grab hold of whatever electrons are floating around in the soup and make neutral atoms, positively charged nuclei, negatively charged electrons. The atoms are neutral, the universe becomes transparent, the light is free to fly across the universe, and that's what we see as the cosmic microwave background. The fluctuations in the cosmic microwave background are effectively an imprint of the dimples in the original golf ball. Once we have atoms, well, hydrogen is now available for making stars. How long it takes to make stars, we're not too sure. After that 380,000 years, how many million years does it take to make the first stars? In other words, there will be some dark ages before the first stars switch on, and we're not sure how long those dark ages lasted. One of the reasons the James Webb Space Telescope is up there is to look back in time as far as possible to try and work out when the first galaxies and the first stars were actually made. Was it 100 million years? Was it 200 million years? Was it less? Was it more? We don't really know. So that's one of the reasons we're trying to look back in time with telescopes like the James Webb Space Telescope. Eventually, after a few billion years, all of the galaxies that we see were made, including, of course, our own. What happens after that? Well, that's, of course, a different story. That's the end of everything, and I'll be telling you about that a little later in the month. But let me leave you by reminding everybody that we don't know everything. There are still some gaps in our knowledge. The jigsaw, which I've been trying to put together over the last few minutes, well, there's definitely some pieces still missing. There are some big questions which we still haven't answered yet. Why did matter win over antimatter? What caused the asymmetry? We know that asymmetry must have been there because if there was no asymmetry, if matter and antimatter were made in equal amounts, they would have annihilated and the universe will be full of light and nothing else. There would be no matter at all. There would be no galaxies, no stars, no gas, no dust. So what caused the asymmetry? Still a big question, unresolved. And what is this weird dark matter that we keep hearing about that seems to be causing galaxies to rotate at what we would argue is the wrong speed? Based on all the stars that we can see and adding up all of the mass of all of the stars and all of the gas and all of the dust, galaxies seem to be rotating at a speed that we wouldn't expect. So something else appears to be out there. And also there appears to be something even more mysterious which is causing the universe to accelerate its expansion. Originally we thought the universe might be expanding and perhaps slowing down under the influence of gravity, but now it appears to be the opposite. It appears to be accelerating its expansion. So in this talk, when I've been talking about the beginning of everything, I've tried to be very careful to talk about everything that we can see. all of the stars, all of the galaxies containing stars and gas and dust and everything between the galaxies. And when I talk about the beginning of everything, I've been describing up to this point the beginning of everything that we can see in the observable universe. But now we think that everything that we can see is only 5% of everything that's out there. The other 95% is dark matter and dark energy. But, as they say, that's another story. Thank you for listening.